Have you ever seen an old rusty gate? Or a rusty car? Iron and steel turn to a red, flaky dust. We call this dust rust. It happens when iron meets water and air. This process seems to happen to all iron things, but what if I told you that is not true? In the city of Delhi, in India, stands a remarkable object. It is called the Iron Pillar of Delhi. This pillar is very tall, reaching over 7 meters into the sky. It is also very heavy, weighing more than 6 tons. It was made a very long time ago, around the year 400. That means it is more than 1600 years old. For all those centuries, it has stood outside. It has endured the hot sun of Indian summers. It has been soaked by heavy monsoon rains. It has felt the wind and the dust of a busy city growing around it. Yet, if you look at it today, you will see something astonishing. The pillar is not covered in thick red rust. Scientists and visitors have been amazed by this for a very long time. According to our modern understanding, an iron object of this size should have rusted away completely. It should have become a pile of orange-brown flakes centuries ago. But the Delhi pillar stands almost perfectly preserved. Its surface is a dark gray, with only very small patches of corrosion. It looks strong and solid. This strange fact has made the pillar famous all over the world. It became a scientific puzzle. How could ancient blacksmiths create something that seems to resist the forces of nature so well? It seemed almost like magic to the people who first studied it. Many theories were proposed over the years to explain the pillar's secret. Some people thought the special climate of Delhi was the reason. They said the air was very dry, which slowed down the rusting process, but other iron objects in the same area have rusted badly, so that could not be the whole story. Other people imagined more fantastic explanations. They wondered if the pillar was made from a meteorite, using iron that fell from the sky. This idea was also proven wrong. Scientific tests showed the iron was clearly made on Earth. The mystery only grew deeper as simple explanations were ruled out one by one. The truth, as scientists would later discover, was not in the sky or in the air. The secret was hidden inside the iron itself. The answer lay in the way it was made. The ancient Indian metalworkers who forged this pillar did not have modern machines. They did not have giant factories. They had small furnaces, charcoal, and hammers. They used a process that was very different from how we make steel today. This old method, which we once thought was simple and crude, actually gave the iron a unique and powerful defense against its greatest enemy, rust. The pillar was not magical. It was a masterpiece of forgotten chemistry and craft. To solve the puzzle of the Delhi pillar, we must look at how ancient iron was made. The process was very different from our modern methods. Ancient blacksmiths did not have furnaces hot enough to melt iron completely. Instead, they used a bloomery furnace. A bloomery was a small clay structure, often built into a hill. It looked like a simple chimney. Blacksmiths filled it with layers, iron ore, charcoal. They lit the charcoal and pumped air with bellows to raise the heat. Inside, a chemical reaction took place. Hot charcoal removed oxygen from the ore. The temperature, around 1200 degrees, was still too low to melt iron. The iron formed a spongy, solid mass. That mass mixed pure iron and other materials from the rock. This lumpy, porous result is called a bloom. When ready, they broke open the furnace side. They pulled out the glowing, red-hot lump with long tongs. It was dangerous work. The bloom wasn't pure iron yet. It was full of other things. The most important was a glassy substance called slag. Slag comes from melted rock, sand and other non-iron ore parts. As iron formed, liquid slag got trapped in the spongy bloom. The bloom also contained a little phosphorus. Trandrit spakarban mafrajais. Turbispinturash. And from the charcoal fuel. Once the hot, spongy bloom was pulled from the furnace, the true craft of the blacksmith began. This was not just about making a shape, it was about transforming the metal itself. The blacksmith and his helpers would place the glowing bloom on a large stone or an iron anvil. Then, they would begin to hammer it with heavy sledges. With each powerful blow, the spongy iron became denser and stronger. The hot, liquid slag trapped inside the bloom was squeezed out, spraying sparks into the air like a firework. The iron was being purified and consolidated by force. To make the iron even better, the blacksmith would often cut the metal, fold it back on itself, and weld it together by hammering it at a high heat. They would repeat. this folding and hammering many times. This was like kneading dough. It mixed the iron, making it uniform and strong in all directions. It also stretched the remaining slag into very long, thin layers inside the metal. These tiny glassy threads created an internal grain, almost like wood. This structure made the iron tough and less likely to snap. Blacksmiths used fire to carefully control the iron's properties. They reheated the metal in the forge many times during hammering. The cycles of heating and cooling changed the crystal structure, making it stronger. Heat treatment was a skill learned over generations. A master knew exactly what color the glowing metal should be for each step. They knew how to make a sword edge hard and its core flexible by controlling fire and hammer. Finally, after shaping, the iron was often given a protective coating. This was not paint as we know it. Blacksmiths would quench in oil or rub with animal fat or rub with beeswax. Sometimes soot from the forge formed a dark, protective layer. This final step gave a dark black finish and sealed the surface. The oil and carbon filled tiny pores, creating a barrier to water. Internal chemistry plus external coating gave the iron amazing durability. The way we make iron and steel today is completely different from the ancient bloomery method. Our modern process is built for speed and massive scale. It all starts in a blast furnace. A blast furnace can be as tall as a multi-story building. It runs non-stop, day and night. Instead of charcoal, we use coke, made from coal. The furnace is filled with layers: iron ore, coke, limestone. Superheated air blasts in at the bottom, raising temperatures above 1500 degrees C, much hotter than an ancient bloomery. At these temperatures, the ore doesn't stay a spongy solid, it melts completely into liquid iron. That liquid iron, pig iron, trickles down. Limestone melts and mixes with impurities, sand and rock. Those form liquid slag. Slag is lighter, so it floats on top. That makes separation easy. Slag is drained off and the liquid iron is poured out. The process removes almost all impurities, producing very pure iron. It contains a lot of carbon, which makes it brittle. To make steel, it must be refined further. Molten iron is moved to another vessel, and pure oxygen is blasted through it. The oxygen burns off excess carbon and impurities. The result? Modern steel. Modern steel, a very pure iron alloy with controlled carbon. We can add elements like chromium, nickel, to make steels with specific properties such as stainless steel. But purity and efficiency came at a cost. Removing slag also removed tiny glassy threads that protected wrought iron. The modern process also removes nearly all phosphorus. Modern steel is chemically uniform and pure. That purity makes it highly reactive. When exposed to air and water, it has no natural defense. It rusts quickly and evenly, forming flaky red layers. For many years, the rust resistance of the Delhi pillar was a mystery, but with the help of modern science, we have finally been able to look inside the metal and find the answer. Scientists took very small samples from the pillar, so small they would not damage it. They analyzed these samples, using powerful tools like electron microscopes, X-ray spectroscopy. These tools allowed them to see the chemical makeup of the pillar's surface in incredible detail. What they discovered was a remarkable invisible shield that has protected the iron for over 1,600 years. This shield was not magic, it was chemistry. They found the surface is covered by a very, very thin layer, only a few millionths of a millimeter thick, too thin to see with the eye. This protective film is not rust. It's a compound called iron hydrogen phosphate hydrate. That name describes a dense, stable material made from iron, oxygen, hydrogen, and phosphorus. Phosphorus, trapped during the bloomery process, played the starring role. Over centuries it reacted with iron, air, and water to form the protective skin. That layer is self-healing. If scratched, the process starts again. Exposed, phosphorus-rich iron reacts with the environment. It doesn't form flaky red rust. Instead, it slowly rebuilds the thin, dark film over the damaged area. Modern steel behaves differently. When modern steel rusts, the layer swells, cracks, flakes off. That exposes fresh metal, which then rusts, a vicious cycle until the metal is gone. The Delhi pillar's film is stable and strongly attached. It acts like paint that never peels and repairs itself. The Iron Pillar of Delhi is the most famous example of rustless ancient iron, but it is not the only one. All across Europe and Asia, we find other iron objects from the past that show the same surprising durability. These artifacts prove that the skills of the ancient Indian metalworkers were shared by blacksmiths in many different cultures. Beautifully preserved swords from the medieval period have been found in tombs pulled from rivers. While some are heavily corroded, others can still be polished to a shine, showing the intricate patterns created by folding the metal. Their survival is a testament to the quality of the wrought iron they were made from. Look at the great cathedrals of Europe. Many are adorned with huge, intricate iron gates, hinges, decorative metalwork. Some of this work is over 800 years old. These objects have been exposed to the damp and polluted air of European cities for centuries. This metal has endured fire and weather, yet it remains largely intact. Like the Delhi pillar, this iron was made in bloomeries. It was hammered and shaped by hand. It contains the same slag inclusions and, in many cases, enough phosphorus to help it resist the worst effects of rust. Even older examples exist from the Viking Age. Viking swords and axes are legendary for their strength and quality. Archaeologists have unearthed weapons from Viking burial sites that are over 1,000 years old. After a careful cleaning, the quality of the ironwork is often stunning. The technique of pattern welding is clearly visible. This process of repeated forging and folding contributed to the metal's resilience by creating a complex internal structure. Let us place the two types of metal side by side to see the differences clearly. On one hand, we have ancient wrought iron. It was born in a small, relatively cool bloomery furnace. It was never fully melted. This process left behind important impurities. Tiny particles of phosphorus were scattered throughout the metal. Microscopic, glassy threads of slag stretched into long layers by the blacksmith's hammer. The surface was not perfectly smooth. It had a texture from the hammer blows. The final object was the result of one person's skill, fire, and sweat. It was a unique, handcrafted piece. On the other hand, we have modern steel. It is born in the roaring heat of a giant blast furnace. It is completely melted into a pure, uniform liquid. The goal is to remove every possible impurity. The phosphorus is taken out. The slag is skimmed away cleanly. What remains is an almost perfect alloy of iron and carbon. It is poured into molds to create identical pieces on a massive scale. The surface is smooth and consistent. The key difference is how they react to the world around them. When ancient wrought iron gets wet, a slow and complex process begins. The phosphorus inside helps to form a thin, dark, and stable protective layer. This layer sticks tightly to the metal and stops rust from going deeper. It is a passive defense. The internal slag fibers also act as tiny barriers, disrupting the chemical reaction of rusting. The metal essentially armors itself over time. Modern steel behaves very differently. Because it is so pure and uniform, it is also very reactive. When it gets wet, the rusting reaction starts quickly and easily. There is no phosphorus to create a protective film. Instead, a layer of red, flaky rust forms, weak and porous, holding moisture and accelerating decay. Modern steel's purity is its strength in construction, but it's also its greatest weakness when it comes to corrosion. It needs constant protection from the outside. The story of ancient iron and modern steel teaches us a powerful lesson. It is a lesson about more than just metal and rust. It is about the difference between craft and mass production. The ancient blacksmith was not trying to make the purest iron possible. He was trying to make the best iron he could with the tools and knowledge he had. Through his slow, careful, hands-on process, he accidentally included the very ingredients that gave his work incredible longevity. The so-called impurities of phosphorus, slag, turned out to be blessings in disguise. We in our modern world often believe that newer is always better. We think that purity, perfection, are the ultimate goals. Our industrial processes are designed to be fast, efficient, and uniform. We have mastered the science of making huge quantities of pure steel. This steel allows us to build amazing things, from cars, bridges, ships. But in our quest for this kind of perfection, we lost something important. We engineered out the happy accidents and the hidden strengths that came from an older, slower way of doing things. Our steel is strong, but it is also fragile in the face of nature. The lesson is not that we should go back to making iron in small bloomeries. We cannot build our modern world with ancient methods. The lesson is about appreciating what was lost. It is about understanding that sometimes imperfections can be strengths. It is about recognizing the deep wisdom that can be found in traditional crafts.